Check test. Check test. Check test. Test. Check test.
Are the mics live? Okay. Oh, you got to talk into just one of them, right? There you go.
Oh, that one's going now.
Now you can hear me, right? Okay.
That one was going just a minute ago.
This one? Okay.
One or the other.
Gotcha.
Yeah, don't do both.
Okay, I'll just go with that one.
Yeah.
Excellent. Okay, it's 7:30. Welcome to the July meeting of the Johnson Space Center Astronomical Society. My name's Chris Wiles. I'm the vice president of the club. That means that Doug, who normally is stood up here, is out on vacation, so I get to stand in during these events. As is customary, what we like to do is ask the audience who is new, who is this the first time that they've been here? Excellent. What we like to say is, how did you find out about us, sir? Meetup.com. Excellent, excellent. Welcome. And do you have a telescope?
No, I do not.
Okay, you need to get one.
I go to Brisbane.
Okay, yeah, you use theirs, absolutely. What you'll find is probably you end up with more than one when you finally get one too.
Yeah.
They accumulate and multiply. So, anybody else new here today? Yes, sir.
I think Al Merrill, is that his name?
Yeah, yep.
He was out at X Bar and he said, why don't you come out to JSC and we meet.
Excellent. We've got somebody from HAS. We got a convert from one club to another. So thanks for coming. Anybody else new here today? Oh, three at the back. You want to just say a little bit about yourself and how you heard about us?
It's actually four of us. We're Dr. David Kring's students at LPI, so we thought we'd come along.
Brought my own audience.
I think this is called the home field advantage, actually. Excellent, excellent. Well, a few slides before we get into the main presentation. This is our agenda here today. The main presenter here is Dr. David King. He's brought his own fan club, Astrogeology of the Artemis Exploration Zone. We've got some regular agenda items that we go through. We've got the What's Up in the Sky by Aaron Thero. Shortly after the break, we've got Star Party news, door prizes, and of course we have our traditional meeting after the meeting where we go to Mod Pizza. So that's our normal, that's our agenda here today. Okay, how can you find out about the club? We got two sign-up lists. One sign-up list is from Ron, who's out there and does the DVD library. So you can actually take a token there or sign up with Ron, and that will actually give you only one email a month that tells you about this meeting. So if you want to sign up and only get one email a month to say, hey, when is our next meeting? That's the list to get on. There's also a more general list that will actually give you information not only about this meeting, but about other events too, such as the Star Party announcements whenever we have a Star Party. So that you get with David Haviland, and there is his email there. So that's how you get on our email list servers in order to actually pick up more information. A little bit of housekeeping in this building. There's something we call the green button blues. Not quite sure of the timing of when the doors change, but if you're going to leave the building and you press the green button, you got 20 seconds to get in and out of that door, or else the alarms can go off. So that's just something to watch out for. Also, while you're in this building, don't go beyond the rotunda area. So there's kind of a private area past there. So just stay within this section of the building. So that's just one housekeeping slide. Reminders to presenters, microphones. Just as I'm learning right now, if you stood here, you talk through one microphone, don't push the two together because it mutes everything out completely because they're out of phase of one another. Or you can use one of these microphones. So if you're a presenter and I like to walk the stage, you can use one of those microphones instead. In terms of it, instead of a laser pointer, we've just left the mouse pointer like this. So you just move the mouse if you're looking to actually point at anything. So that's a little information sheet there for presenters. With that, let's turn ourselves over, and I welcome Dr. David King, senior scientist here at LPI, who has the home field advantage today and his own fan club. So welcome, Dr. King.
Thank you, Chris.
Okay, well, thank you again for having me. I think this is the second, maybe even the third time I've spoken to this group, so it's kind of nice to revisit with you. I'm going to be speaking about the Artemis Exploration Zone. I'll be introducing that. There's a little picture of the lunar surface there on the bottom of the slide that shows the South Pole. And so if you are an astronomer, you recognize that's the correct view of the moon. Nobody's laughing. Isn't the moon inverted in your telescopes? Yeah. Okay. So anyway, I'll be talking about the Artemis Exploration Zone, and I want to begin by introducing this term astrogeology. It's kind of an old term, and it actually begins with a telescopic survey of the moon. This was a picture from the Consolidated Lunar Atlas. This is an atlas that was created from the Catalina Sky Survey, a 61-inch telescope north of Tucson. And the astronomers were absolutely critical to the pre-Apollo phase. They generated our first maps, if you will, of the lunar surface. And so there was an astronomical component to the exploration of the moon. Of course, that led to the eventual landing on the lunar surface, the Apollo 11 landing. And that, in turn, allowed geologic samples on the lunar surface and bring them back to Earth. Here is sample 10003 in the curation lab here at JSC. Actually, this picture was taken in what's now Building 37, which was the original lunar receiving laboratory. All of these samples are now in Building 31. And my own path is quite similar to that. When I was a student, there wasn't a field of planetary science, which we do have today. I spent the first half of my career teaching at the University of Arizona in a department of planetary sciences. But when I was a student, such a thing did not exist. And so if you were interested in pursuing studies of the lunar surface, interested in analyzing those samples that Neil Armstrong and Buzz Aldrin collected, you had to study both astronomy and astrophysics and geology. So you had to do double majors. So though I consider myself primarily a geologist, I do have roots in astronomy and astrophysics. I did a lot of work at the Kirkwood Observatory, which was a 12-inch Warner and Swayze refracting telescope, looking at the moon and making a lot of observations of asteroids. I spent a lot of time in particular looking at asteroid 9 Metis. in turn provided me an opportunity to start analyzing the Apollo samples. I began looking at Apollo 15 green glasses, which you see here, which are a wonderful product of volcanism that occurred on the lunar surface a very long time ago. So that is a short introduction to what we mean by astrogeology. It was this field of planetary sciences that emerged from this integration of astronomical observations of planetary objects and actual missions to the surfaces to begin collecting geologic samples. Okay, so now let's begin to talk about the Artemis program. And whenever I talk about things like this in an audience in Clear Lake, it's a little bit terrifying. You know, sometimes there's an astronaut in the office, a flight director, you know, 2 or 3 flight controllers. So you have to understand that this is a geologist talking about rockets. Okay, but I do want to just introduce the sequence that we have right now. This is Orion's path to human space exploration. This is a NASA illustration. We had a pad abort test, we had the exploration flight test, we had the ascent abort test, and most recently we had Artemis 1, the Orion crew vehicle around the moon and returned it at rather high velocity into the top of the Earth's atmosphere. We're now in the midst of planning for Artemis 2, which will be the first crewed mission, and 4 of our friends and neighbors have recently been selected for this particular mission, scheduled to go next year. So everything is starting to pick up in pace. And much like the Artemis 1 mission, they will go swing around the moon and return to Earth without touching down. The first surface mission, Artemis 3, that'll be our 7th human landing on the lunar surface. That's scheduled right now for 2025. This will carry the crew to orbit, and then they will descend in the human landing system, and which in the case of Artemis 3 is going to be built by SpaceX. Cadence of landers to the lunar surface. We have an HLS uncrewed demonstration of SpaceX Starship, which is scheduled to be next year. Then we have the Artemis 3 landing, which will be the second use of that Starship vehicle. And SpaceX has also been given the contract for Artemis 4. Recently, NASA selected a second company, Blue Origin, to provide a second lander. And Blue Origin's HLS uncrewed demo will be in 2028, and their first crewed landing will be in 2029. So if you're a geologist and you would very much like to see geologic samples return to the lunar surface, it's very good, very pleasing to see this fairly rapid cadence of missions to the lunar surface. So where are they going to go? The vice president or the previous vice president selected the exploration zone for us. It is going to be in the South Pole. This is a view of the lunar surface far side. This is a topographic map of the far side, southern hemisphere. And there's a very large basin on the far side. It's called the South Pole Aitken Basin because it stretches from the South Pole to a very tiny crater called Aitken on the other rim. And it's about 2,400 kilometers across. So that's continent size. It's a very large impact basin. It's the largest and oldest basin on the lunar surface. There is a discussion as to whether the northern hemisphere of Mars is an impact basin. If it is not, then this is the largest impact basin in the solar system. So Artemis is going to be exploring that South Polar region. Not much of the South Pole Aitken Basin, at least initially, but all of the activities are going to be centered around the South Pole. And here is another astronomical view of the South Pole. So I hope some of you have had an opportunity to look at the limb of the moon with your telescopes. The detail that you can see is absolutely extraordinary. This is an image that was captured Tom Glenn, and I can't recall the year. It may, 2018, I see there it says. And so the South Pole is at the top. It's surrounded by a number of impact craters, and that's actually one of the punchlines of this particular slide. This is an impact crater terrain. It's not one of the relatively smooth volcanic terrains that Apollo 11 and 12 visited. This is going to be topographically complex. So we have a series of craters: Amundsen, Faustini, Shoemaker, Shackleton, de Gerlach, all named, as you might recognize, for polar explorers here on Earth. Those craters are interspersed with mountains, which we call massifs on the moon, that were uplifted by the South Pole Aitken impact event that I pointed out in the previous slide. And so we do have mountains, one of which is called Mons Malapert, and I believe that's labeled up there. Adjacent to it is Mons Muten. And these mountains, I should point out, were observed telescopically early in the 20th century. Ewan Whitaker in the UK mapped them out, publishing reports to the monthly reports of the Royal Academy of Sciences, in the UK, and described the Sleipnitz mountain range. And this mountain range was recognized as being a curvilinear structure. And so it was hypothesized from the short arc visible in the polar regions to be part of this immense impact basin, which was later recognized when the Soviet Union provided images of the far side. And of course, lunar orbiter missions from the United States also captured the far side. Okay, this is a plan view of that exploration zone. The crosshair is on the South Pole, which happens to reside right on the rim of the Shackleton impact crater. The Artemis exploration zone, or at least the initial Artemis exploration zone, is defined as the region from the South Pole to a latitude of about 84 degrees. Okay, and so that's an area roughly 360 kilometers in diameter, roughly the distance between Dallas and Houston. And NASA has selected 13 candidate landing regions for the Artemis 3 mission. I'll have the next slide will show where those candidate regions are. On this chart, there are a number of triangles, red and white. These are all landing sites and traverses that have been studied right here at the LPI over the last decade in preparation of these Artemis missions. I should say that why we've been mapping these potential landing sites and EVA traverses, we've encountered a large number of craters that do not yet have names, okay? And to facilitate discussion in the science community and with our engineering colleagues at JSC, we've had to strategically put a few names on these craters. It becomes very cumbersome in a conversation, as you can imagine, saying, we're looking at this crater to the left, and depending on what side you're approaching it from, the left might be different. So we've put a few extra names on craters in the South Polar region. We've named one crater Henson. Henson, with Commander Perry, was the first in historical times to reach the North Pole of Earth. Dr. Ursula Marvin, she was one of the original analysts of the Apollo 11 samples. She's a co-author of what's called the lunar magma ocean hypothesis. She was the first woman to serve on the United States expeditions to collect meteorites in Antarctica, and I could go on and on and on. So a crater's been named for Ursula Marvin. And then a crater's also been named for Dr. Anna Jonas Stoss, who was one of America's first female geologists. She mapped most of the Appalachian Mountains. It is said that she mapped more of the Appalachian Mountains than any geologist that has ever lived. So it was quite a remarkable career that she had. Okay, this is... Oh, I don't recall. Okay. Don't recall. Yeah, don't recall.
I only ask because that's my name.
Ah, okay. Yeah, I don't recall. There is a book, actually there's several editions of books that have been published that give you short bios of all of the names of craters on the lunar surface. But of course, today you Google it and Wikipedia will have something for you. Okay,
Dr.
So-
Kring, I have a question from online. Do you have a minute?
sure.
When sampling a crater, how do you distinguish material between moon surface and the colliding meteor?
Oh, the moon is a differentiated planet, which means many of the denser iron-related elements have been either sequestered in the core or were actually lost in a giant impact that produced the Earth-Moon system. So it has a really evolved chemical composition, a primitive asteroid or comet. So the chemistry makes that actually very, very easy. Yeah. Yeah. So an important point to take away when thinking about the lunar South Polar region, this Artemis exploration zone, is the topography is dramatic. And this is a view that some students produced, I believe it was last year, showing obliquely the lunar South Polar region. And this isn't an actual image. What they have done is they have mapped out the maximum amount of or the average illumination for, throughout this zone. So areas that are dark have very low average illumination, and in some cases zero illumination. And the brightest areas typically are on mountain summits that are exposed to more sunlight. But as you'll see in a moment, the sun is circumnavigating the pole, which means it's constantly casting long shadows, which makes it difficult to appreciate the topography in an image. You have to create the synthetic illumination to actually appreciate the depths of the craters and the elevations of the summits. Okay, so how high are those summits and how low are those craters? So here is a cross section that I made there on the left that looks at the elevation over Leibniz Beta. That's now called Mons Mutten. That is the tallest peak on the moon. It's in the South Polar region, and adjacent to it is Shoemaker Crater. And then for comparison, I have the topography of Mount Everest. And so as you can see, the elevation change from the summit of Mons Mutten to the floor of Shoemaker is as dramatic, if not more so, than Mount Everest is above sea level on Earth. Okay, I'm going backwards. Okay, so let's zoom in a little bit on that South Polar region. Again, the cross here, it is right on the rim of that crater called Shackleton. In this map perspective, and this is now the traditional, isn't quite the right word, but anyway, this is the orientation that we now utilize. In this perspective, the near side is in the top half of the image. And I should point out that due to topography, not all of those near side locations have direct line of sight to Earth, which is one of those features or parameters that's of interest to mission architects. We would, of course, like to maintain communication with crew on the lunar surface at all times. You'll see that Shackleton Crater is a nice bowl-shaped crater. I mean, it looks like your cereal bowl, right? And so we call those simple craters. And so this is much like Meteor Crater in Arizona, which we use to train astronauts. This is an oblique view of Shackleton Crater. SP is, again, the South Pole. That crater is about 21 kilometers across. And when it was produced, it cross-cut this mountainous ridge, this massif that is running towards you in the foreground. There's two site numbers, site 004 and site 001 in that diagram. These are 2 points that are relatively high summits, and they are illuminated about 85 to 86% of the time. And so if your mission architecture is driven by access to power, these are attractive places. You have a lot of solar energy. At all of the Apollo landing sites, they had 14 Earth days of sunlight, but then they had 14 Earth days of darkness, which would make long-term exploration a bit more of a challenge than it would be in these locations. This is a cross-section that we've made of Shackleton Crater. Geologists like to think about the subsurface, not just what is at the surface. And so the south on the left, you can see it has this very simple bowl-shaped morphology. There is a dotted line across it, and there's a gray area beneath that dotted line, and that's to illustrate that because the sun is circumnavigating the pole, it is casting these long shadows, so much so that the interior of Shackleton is permanently shadowed, okay? And it gets very, very, very cold within that permanently shadowed region. Now, I don't know if you know much about impact cratering, and so I've put this computer simulation that we did for the formation of Shackleton crater, and we had to explore parameter space. You know, we adjusted the impact speed of the object. We looked at asteroids of various densities. We looked at a few comets, and of course, there's a trade-off between the mass of the object and the velocity of the object. You have to get the kinetic energy just right to excavate the crater. But here is what that impact would have looked like. And you can see as the crater was excavated, it threw up a tremendous amount of debris that we call ejecta. That debris then was ballistically carried out of the crater and landed on the surrounding landscape. And so one of the takeaways from this model is if the astronauts are, for example, landing on and exploring that ridge that I pointed out in the previous slide, they are going to be walking on and sampling ejecta from this particular impact event. Now, because we did explore parameter space, we were able to say that the asteroid had a diameter of about 1.5 kilometer, and it's a stony asteroid, not an iron asteroid, and it hit with an impact velocity of about 15 kilometers per second. Okay, now, this is Meteor Crater. I said Shackleton Crater is very much like Meteor Crater in form. This is a nice, simple bowl-shaped crater. This is the world's best preserved impact crater. And so people in my business go on pilgrimages to Meteor Crater to take a look at it. And I do invite you to go to the Meteor Crater. It is a wonderful site. There's a little museum on the northern edge. It's easily accessible, just 6 miles south of I-40. It's between the Petrified Forest and the Grand Canyon, so there's a lot to be seen there if you are interested in taking a family vacation. Okay. Because it is the world's best preserved impact crater, it's no surprise that it's commonly used for astronaut training. Gene Shoemaker, you see there, is training a group of Apollo astronauts, and there's a picture of myself where we continue to train astronauts today. So there is a very big difference, though, big being the operative word here, between the scale of Meteor Crater and Shackleton Crater. So Meteor Crater is about 1.2 kilometers across, and Shackleton is about 21 kilometers across. To give you a better feel of what 21 kilometers is like, here is a picture of Shackleton Crater with a map of our highway system on it. So here we are, there's the Johnson Space Center. We're way down here in the lower right-hand corner. You see the 8 Beltway, you see the 610 Loop. And so how many of you have driven around the 610 Loop? Okay, 2/3 of you, 3/4 of you. So you have some idea now of the circumference of Shackleton Crater on the lunar surface, okay? Now, there's another perspective in geography that oftentimes get lost when you are looking at spacecraft images of the lunar surface, and that is this parameter called depth. Geologists look at this and they immediately have an intuitive sense of exactly how deep this crater is, but most people do not. And so to illustrate that, I have a comparison cross-section of Shackleton Crater with the Grand Canyon. Okay, so there was some early discussion with some of my colleagues about landing astronauts on the rim of Shackleton Crater, and the astronauts then walking down to the floor of Shackleton Crater, collecting a few samples and walking back up to the lander, and they're not going to be doing that. So if you've been to the Grand Canyon, if you've hiked the Grand Canyon, you know, I can get down to the floor of the Grand Canyon and back in about 6.5 hours, but that's not in a spacesuit. Yeah, I don't think anybody's going to be doing that. So in a crater terrain, oftentimes you're going to have to make the decision. You will outside the crater and explore the surroundings, or you are going to land in the center of the crater, the floor of the crater. You're not going to, in general, be landing in one place and exploring the other. Okay.
Dr.
So-
Crane,
Yes.
we have another online question if you have a moment.
Mhm.
How and when do you decide what's most interesting to investigate with so much to choose from?
Why don't we save that one to the end?
Okay, sounds
Okay.
good.
All right. So the impact cratering processes that I've been describing has in large part created this topographically dramatic terrain. Okay. And as I said before, the sun is circumnavigating the South Pole. And so here's an illustration showing the position of the sun in 4 quadrants. And you can see that if you do have a topographic low, that there can be in the center of that topographic low an area that absolutely never sees the sun. And those we call permanently shadowed regions, and they're very cold, and they're places that may be traps for the small amount of volatiles that exist on the lunar surface. And so there is some hope in the lunar community that there might be the prospect of recovering ice in these terrains. Now, here is a little movie over the course of 1 year that shows how those shadows are rotating around the South Polar region. Right in the center of that image is the Shackleton crater. If you are doing a long duration mission, that is a mission on the scale of a year or longer, these shadows are something that you're going to have to contend with. We've looked at the movement of shadows over the time period of a typical EVA, an 8-hour EVA, and the shadows are significantly in that period of time. Okay. All right. So what is it like if astronauts launch from Earth when the Artemis 3 crew launches and they go to the South Pole? They're going to be seeing a part of the moon that we've not seen before. And hopefully this will be the first mission in a large number of them that will allow us to explore this region. So again, there are the names that hopefully are becoming familiar to you. I suspect once the mission, we get Artemis 3 and Artemis 4 in our belt, everybody is going to know these names. And again, you can see Shackleton crater right there in the center. So what is that 7th landing? What is Artemis 3 going to be like? And here I am simply quoting from the Human Landing System Concept of Operations. This is the information that is publicly available. So they are going to be spending 6.5 days on the surface, which is longer than Apollo. They will be conducting at least 2 EVAs and potentially 5 EVAs, okay? Each of these EVAs is to be at least 4 hours long, with nominal EVA durations being 6 plus or minus 2 hours. Importantly, for those of you who remember Apollo 15, 16, and 17, or are used to seeing pictures of the astronauts driving over the lunar surface during Apollo, they're not going to have that type of vehicle in Artemis 3. So these are going to be walking EVAs. They're going to be limited to a distance of about 2 kilometers from the land. They're going to be very much like the Apollo 12 and Apollo 14 missions. Now, here are those landing regions that they're going to be landing in one of these patches, okay? At least that's the plan now. We're hoping that NASA is going to announce a descope of these 13 sites to some smaller number, like 3 to 5, by the end of the summer, so that we can focus our research on a smaller number of sites. Our team here at the LPI and our academic colleagues have actually studied at some level all 13 of these sites. We have spent more time studying some of these sites like Connecting Ridge, which I've already illustrated for you this evening. Within each of these candidate landing regions, there are multiple potential landing sites. Okay, so you should not equate landing region with landing site. In some of these, there might be 6 or 7 landing sites, possible landing sites. And so there has to be not only a trade between these candidate landing regions, but there is also going to be a trade between landing sites within these regions. And one other thing that I want to say that is not going to be obvious to most people is that the launch window has a dramatic effect on which of these sites you can go to. And so if there are sufficient delays in the launch, the primary landing site may be missed and they are going to have to go to another one. And so that's one of the reasons that we're carrying multiple candidate landing regions and landing sites at this moment. And we will probably have to do that right up until the launch of Artemis 3. Once they're all clear of the pad, we'll know which site, of course, they're going to. And the Artemis 3 geology team will then be able to focus their attention on that landing site. Okay, so I want to say just a little bit more about the geology that they might be able to do, which is why I didn't answer that question earlier. I'm going to say a little bit about what options they will have. And, you know, to do this in any great amount of detail, we would have to actually know what the landing site is. And as I've just described, we don't and we won't until quite late in the game. And so I'm just going to assume for the purposes of illustration in the next couple of slides that we are landing near the South Pole, okay, on the rim of Shackleton Crater or on that connecting ridge adjacent to Shackleton Crater, okay? And so and so here's an image of that region. There is a 100-meter scale bar on the image left. You can see there's a small crater with some ejected material. There are boulders on the surface. There's actually an outcrop, and an outcrop's not just a rock sitting on the surface. This is a bigger rock structure that actually hopefully may have some information, textural information about the processes that produce the material. It's also casting a shadow. That actually might be a small permanently shadowed region. It's small enough that we actually don't have enough data to say whether it is one way or the other confidently. So this is a very good candidate for astronauts to walk up to and take a couple of hammered samples off of those boulders. And we've done this type of process, as I said, in most of at some level at all of the candidate landing regions. And so in some of these areas, our studies have such high fidelity, we know what rocks we want the astronauts to sample if they land in that area. So that's kind of an exciting place to be. Here is another picture of another area. Again, there's a 100-meter scale bar on the bottom, and there is this huge rock exposure. So it's in excess of 100 meters. Oh, we never saw a rock exposure that size at an Apollo landing site. And so the geologists, you know, are just salivating over this type of thing. This is like the expanse of rock that you see in an interstate outcrop. You know, you drive by and there's just rock, 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 rock. And every once in a while you'll see a car parked there. That's a geologist. and there is just so much rock exposed there. You get a very much better picture of the geologic evolution that's involved in that. If it is an igneous rock, that is, it intruded into the crust of the moon at depth, you'll get a much better picture of the crystallization of that magma chamber. It's just, this could be a game changer in our understanding formation of the lunar crust of the moon. Okay, and so the astronauts are going to come back with boxes of rocks. So here's an example. This is Apollo 11 samples, and I know a lot of people. I sometimes hear it when people don't know I'm too close. Oh, we're going to get more gray rocks, more gray rocks. Nothing could be more boring than more gray rocks. Okay, that's just not true. Okay, so I'm here to enlighten you. All right, so. If you're a scientist like me, you get to work in a lab like this, or you get to work in a lab in some of the labs over in building 31 at JSC. You get to take thin slices of these rocks and you actually get to peer inside them. And this is what that looks like. So this is a thin section of one of those rocks. And by a thin section, I mean that we take a very thin slice, we mount it on optical grade glass, and then we polish it. I used to tease my colleagues in the astronomy community that we polish it better than you do your lenses and your telescopes. And then we put this on it's 30 microns thick, that's our standard thickness, and then we put it on a microscope and we either transmit light through it, which we see here, or we reflect light off of it, okay? And in this particular view, we've put crossed polars above and below it, or so we have a light stream coming up through the microscope, and I'm taking a moment to describe this because you work with telescopes, which are akin to microscopes. So we have our glass plate and rock sample here. We're transmitting light through it. Before we get to the sample, we have a polarizer. The light then goes through the sample, and then it goes to another polarizer that's crossed, okay? So if that sample was not there and we tried to put light through those two cross polarizers, what would you see at the eyepiece? Nothing, absolutely nothing. But when the light goes through the minerals between those two cross nickels, those two cross polarizers, the light is bent. And the type of mineral will bend the light different amounts. And so a geologist picture and says, oh, I see the mineral olivine, I see the mineral plagioclase, I see the mineral pyroxene, I see the mineral ilmenite, simply based in the way that that light is being bent between those two crossed polarizers in the sample. So this is a wonderful sample. This actually is a basalt sample. This is an Apollo 12 sample. This is another basalt sample. This is from Apollo 17. This here is dominated almost exclusively by the mineral olivine, except for those black patches. That's the mineral ilmenite. This is an iron titanium mineral. And some of the people in the ISRU community, the in situ resource utilization community, just love this mineral because they can make water out of it. And at the same time, extract that titanium, which you can then use in a 3D printer that the Marshall Space Flight Center has built to make for your spacecraft. Okay, and then last, here's another view. This is an impact melt breccia. So this is made by one of the big impact events on the lunar surface. It remelted the rock in the lunar surface, which then cooled and recrystallized to form this texture. It looks like stained glass, okay? And so I hope these are the pictures you carry in your mind the next time you hear somebody say something derogatory about those gray rocks. Okay, so these rocks are really important. They were really important in Apollo, and they're going to be even more important during Artemis. You know, when you tune into shows on Discovery or on Nova and you hear about these really extraordinary things about lunar evolution, that came from a study of Apollo rocks, okay? So here are some of those big ideas that you will oftentimes hear about. The giant impact hypothesis for the origin of the Earth-Moon system. The lunar magma ocean hypothesis that postulates that the moon was once surrounded by a sea of magma that eventually crystallized to form the crust that we see today. There's the lunar impact cataclysm hypothesis, and I'm going to come back to that, expand upon that in a few moments. Then we have the impact origin of life hypothesis. We think that this early period of bombardment may be involved in the early in the origin and early evolution of life on our planet. There's two new, relatively new hypotheses. The lunar magmatic epoch hypothesis that postulates that this giant South Pole Lake and Basin impact event on the far side, which I've shown you, actually perturbed the mantle on the near side, causing a period of magmatism, and that actually may have produced most of the igneous rocks that that the Apollo astronauts collected. And then we now have new techniques that allow us to analyze, detect and analyze water in lunar samples. And so that's allowing us to study the origin and source of lunar water and also water in general to the Earth moon system. Okay. So putting all that together, this is our view of the early moon. That's the South Pole Aiken impact event. Then we think there is an intense period of bombardment. Okay, so I'm going to say a little bit more about that lunar impact cataclysm hypothesis because there has an astronomical angle to that story. And so I do need, again, to go back to those Apollo samples because the astronauts collected a lot of impact-related lithologies, rocks on the lunar surface, and returned them to Earth. We were able to analyze them, including the ages of those impact events. Here is a table of, I think it's 15 or 17 of the youngest impact basins on the lunar surface. And when I use the word impact basin as opposed to crater, I mean an impact structure that's 300 kilometers or larger in diameter. So there's the diameter, and you can see the smallest is 300, and some of them are up to 1,200 kilometers in diameter. That's a fairly hefty structure, particularly when you remember that the Chicxulub crater on Earth, which extinguished most life on Earth 66 million years ago, is a puny 180 kilometers in diameter. Okay, now because the Apollo astronauts collected those samples, we have a few ideas as to what the ages are of those impact basins, and the punchline here is all of those basins seem to have formed in a period of time less than 100 million years. So that's a lot of impact events, some very large impact events in a very small amount of time. Okay, and so that is the origin of this lunar cataclysm hypothesis. This is a chart showing the flux of impacting asteroids and comets on the y-axis as a function of time from 4.5 billion years ago to today. When the Earth-Moon system was forming, the collisional rate would have been quite high, and then it decreased to some lower level today. Thankfully, it's a low level today. And then there seems to have been some type of perturbation there around 4 billion years ago. Now, I have to say that there is still a great amount of debate on the magnitude and the duration cataclysmic bombardment. And so that's one of the reasons we need to go back to the lunar surface. But that said, there is a consensus that that period of bombardment ended about 3.8 billion years ago. There are all these unanswered questions, and here's just a few of them. What happened between 4.5 and 4.1 billion years ago? What was the source of the impactors? What were the effects of those of that basin forming epoch on the Earth and the Moon's orientations? You know, did it change the spin axis? What was the source of bombardment imply, or what does the source of bombardment imply about solar system orbital dynamics? Okay, and that's the point I wanted to make for this particular group. This is a picture, an illustration, a cartoon of the solar system, or a part of the solar system. There's the Earth with the orbiting Moon. There's Mars, there's the asteroid belt, there's Jupiter, and there's Saturn. And this is before the cataclysm, before that period of impact bombardment. And then this is what we think the solar system looked like after that period of bombardment. We believe that Jupiter's orbit moved, as did some of the other, or all giant gas planets. That caused resonances to sweep through the asteroid belt. Those gravitational resonances started exciting and kicking asteroids, some of which went out of into the far reaches of the solar system, but many went into the inner solar system and hit Mars, hit the moon, hit Earth, and so on and so forth. So what evidence that we have from the Apollo samples suggests that we had relatively late in solar system history, a little bit of a reorganization of the orbits of the gas planets, and that caused this period of bombardment. And obviously, that's a pretty big deal. And so we would really like to test that idea further with samples on the lunar surface and work out some of these additional details. So we can, for example, with some of these lunar samples, actually determine what kinds of asteroids or comets were producing those impact craters. And that will then tell us something about the source region. That in turn will tell us something about the perturbations in the outer solar system that may have caused it. Okay, and so this is a perfect example of astrogeology. By carefully selecting rocks on the lunar surface and returning them to Earth for analyses, the geology, we will be able to discern details about the accretion and orbital evolution of the outer solar system planets and their displacement of asteroids and comets, including those dispersed to the Oort cloud. That is astronomy and astrophysics. Okay, so close with a quick rundown of how the Artemis exploration zone compares with the Apollo sites. And one of the important is the age of that terrain, okay? And so here on the x-axis, I have again a time from 4.5, in this case to only 3 billion years ago, okay? Here are the ages of these surfaces that were explored by Apollo 11, 12, 15, and 17. And then here is the age of the surfaces explored by the Apollo 14 and 16 crews, okay? Here is the age of the Artemis exploration zone. And so we are going to be able to peer deeper in solar system history to work out some of the earlier details. Now, the left edge of that is the approximate age of the South Pole Aitken Basin forming impact event, which resurfaced that South Polar region. Within the impact debris created by that impact basin and some of the other impact craters, we anticipate finding small fragments of crust from an earlier epoch of lunar history. And to again remind you about how old these are, here's two arrows that indicate the age of the oldest surviving rock on the Earth and the earliest isotopic evidence of life on our planet. So we are looking far deeper in time than we can on our own planet. And so we're going to get a very close look at that first billion years of solar system history when, I might remind everybody here, the moon was much closer than it is today, because the moon formed just outside of the Roche limit and has been moving away from the Earth ever since. Okay, and so with each step, Artemis astronauts will be kicking up dust that has accumulated for 4 billion years, stretching back to a period on Earth for which there is no rock record. Artemis astronauts will be picking up rocks older than Earth's continents, and if they are lucky, might actually discover the oldest vestiges of our planet that were ejected by similar impact events on Earth during that same period of impact bombardment. Okay, so with that, I want to thank you, and I will take questions. And yes.
We have one more from online. Do we have seismic detectors on the moon? If we did, could they detect impact events from the far side of the moon?
Well, during Apollo, we did deploy seismometers, and they were active for many years. In fact, including after the Apollo missions. And yes, I believe 96 impact events were detected by the seismometers while they were still operational. There are certainly plans to deploy seismometers with future missions, and in fact, the first one may be deployed on one of these commercial lunar services payload missions that a new way of doing business that NASA is pursuing. And there is going to be a mission that lands in the Schrodinger impact basin. It's close to the Artemis exploration zone, but just outside of it. And that mission is going to deploy a seismometer. Yeah.
Oh, got one right here for you. Did I hear you right that impact basin is actually smaller than Mare Imbrium?
Oh, no. The South Pole Lake and Basin's 2,400 kilometers in diameter. Imbrium's 1,200. Yeah. And so
When I do dome tours at the George, I tell people that's the biggest impact crater on the moon, and now I feel like I'm lying to them.
the South Pole Lake and Basin is definitely bigger, and you don't want to make the mistake of saying it's bigger by a factor of 2.
Okay.
The diameter may be larger by a factor of 2, but it is a 3-dimensional structure.
Gotcha.
Okay, so
Shifting over to
2 cubed, about 8 times the volume.
all right. Shifting over to Shackleton. How you said that it's 21 kilometers across. How old is Shackleton? Because I'm noticing in none of your depictions there's not any remnant of a center spur peak. So I'm figuring that's probably hit earlier.
Okay, so before I answer that, let me say something about crater morphology and make sure everybody's on the same page. So I did say that it was a simple crater. That's a simple bowl-shaped morphology. When craters get bigger, you begin to get the uplift of a central peak, okay, and we call that a complex crater, a central peak complex crater. When they get even bigger, that central peak rises and the rock is not strong enough to maintain that mountainous height, and so it collapses into a peak. And so then we have a peak ring complex crater. Simple craters on the moon are generally 18 kilometers or less in size, but it really depends, that transition to complex craters depends on the strength of the rock, okay? And as it turns out in the South Pole, Shackleton crater being 21 kilometers is still a simple crater. It was always a simple crater. So it's just one of the largest of the simple craters on the lunar surface. So it did not have any central peak, and the central peak's not eroded. It is a relatively young crater on the moon. It's one of the younger craters, large craters in the South Polar region. There's still some discussion on the age of that crater in the scientific community. Our own group has estimated it to be 3.43 billion years old. I think that's the number. Is that right? Okay. Waiting for a mic. Yeah.
Yes. There implies that in the shadow there's scattered light. You can see the astronaut's legs and all that. But I've read transcripts and other lunar scientists say the shadows are so black you really can't see. And we're wondering about where I work. Can you really see in the shadow the terrain, slope, depth, texture, rocks in the way? Can you really see like this?
Yeah. So actually, I'm old enough. I had the good fortune of talking with most of the Apollo astronauts at various times over the course of my career, and so no, they're able to see in these shadows. So Apollo 16 and 17 missions specifically identified these boulder shadows, and the astronauts went into them. They collected samples in them to see if they had additional volatiles compared to the regolith next door. So for example, John Young and Charlie Duke were the first to go in Apollo 16. They saw everything perfectly. There was no physical anomalies that they noted. One of them actually got on their knees to collect the sample. But those are small. Yeah, so scattered light is very effective into these small areas. In the Artemis exploration zone, there can be shadowed areas that are permanently shadowed that are 20 kilometers across or larger. There, you're not going to have much scattered light. Now, we've actually used this, the scattering of light to illuminate some of the smaller craters in the South Pole region. In fact, we made headlines last year. There was headlines called Shadow Games. We were able to use, for example, light from the upper walls of craters that bounced in to actually illuminate areas that had previously been interpreted to be completely black. We had to do some fancy manipulation of the data, boosting the signal, reducing the noise. But we were able to image, I think 43, if I recall correctly, 43 different of the small permanently shadowed regions in the South Polar terrain. So the question to your answer is they can see fine on these small ones, but the big ones are another beast altogether. And there, we have to keep them alive in these incredibly cold temperatures. So the temperatures are going to be 50, 40 Kelvin. Okay. So that's really cold. The requirements for the new spacesuits that are being built is to keep crew alive for 2 hours in a permanently shadowed region. So that's kind of the limit of exploration for Artemis 3. If you want to be doing something more extensive, like go 10 kilometers into one of these PSRs with humans, then there's a whole nother engineering exercise to make that happen.
Hello? Yeah, it's working. My question's, as you bring these samples back, and it was interesting the way you were talking about, hey, we're going to see a lot of these minerals and some are good for this and that and everything. Is there a group of engineers that are going to be just waiting for your report? And when you say, hey, we're finding this mineral or that mineral, they're saying, hey, for the mission, we need to be able to find those because we can do things with that.
Well, yeah. So in geology, we kind of have people and spend their time on what we call basic research, basic geology, and then we have the applied geologists. The ISRU specialists are basically applied geologists, so they're generally speaking always incorporated in the team. So they're not going to be in some distant out of the way place. No, there's going to be good communication. So I don't foresee that being a problem. And built into the mission plans may be ISRU related tests. So if you are, I've mentioned volatiles only in passing, but there's going to be some interest as to whether there are volatiles and if so, at what depth. Okay, well that may then require trenching, or it may require drilling, and so that will be built into an EVA plan. Yeah.
Why was Shackleton Crater, the crater right at the South Pole, named for someone who never made it to the South Pole? While I noticed on the map that there are Amundsen and Scott craters nearby.
Yeah, I do not know the history of this, but let me say something about the naming protocols. It's not like that I can just draw a map and publish a paper and put a name on something. That's not how it works. So the first criteria is that there has to be a legitimate scientific need to put a name on a structure. Okay, and if that name exists, and I explained in our case, the need was we're looking at landing sites and trying to look at traverses, and we just had too many unnamed craters. So then there are sometimes formal and informal naming conventions. In the case of the South Pole, there is an informal tendency to name things after polar explorers, but it's informal and it's non-exclusive. If somebody wants to suggest a name for a particular structure, then they have to write up a notification for that. And then that goes to, in this case, a lunar subcommittee of the International Astronomical Union. It is agreed by countries around the world that the IAU is the authority for putting names on the moon and elsewhere in the solar system. So there's a series of processes that you have to go through to put a name on it. I don't know who put the name, suggested name Shackleton. I do not know the story behind it, but it wasn't haphazard. Somebody had to put some thought into it. And it may have been as simple as Scott and Amundsen are big craters. It may have been they were already named before Shackleton was seen, because Shackleton is a pretty small crater right at the South Pole, not in a lot of images before the Clementine.
All right, let's take one more and then we'll move on.
Question. Excuse me, I had a question about, mentioned that there wouldn't be any rovers on the Artemis missions. It looks like they have a
No.
very big lander, isn't it?
No, Artemis 3 will not have a
Oh,
rover.
okay.
Right.
And
So
then you also mentioned that the northern hemisphere of Mars was not, well, its low elevation was not related to being an impact area.
there are people in the community who argue that low elevation is a giant impact basin. Okay, and I couldn't off the top of my head tell you what their reasoning or rationale is. Yes, yeah. Okay, my pleasure. Thank you very much for having me.
Okay. Very exciting. Very exciting where we're going to land back on the moon. So next agenda item is Ron here?
Oh, I'm here.
You want to say a little bit about the Lona Library?
Yeah, we have like 200 DVDs. You're more than welcome to. You're not going to find them online. And the Infinite Cosmos series, which is 80% of the DVDs, is actually brought to you by Astronomy Magazine. They're about 45 minutes long. You'll see on the left up there, of course, we also have the great courses. And those, of course, are 10, 11, 12 hours long. So, but you're more than welcome to take them out. We've also got a couple of star atlases. I think we have 3 planispheres and moon maps. So anyway, thank you.
Thank you, Ron. Okay, a little bit about the meeting after the meeting. Not coming up yet because we've got a second part of the meeting, but this is the place we all like to go to after the meeting. Meeting finishes at 9:30, so we got almost an hour, 50 minutes or so. But it's straight down Middlebrook Drive, left on Clear Lake City Boulevard, and right next to the HEB. That's where we go to the Mod Pizza afterwards. So do join us for Mod Pizza after this event. Okay. So now we're going to just go into about a 10-minute break before we go to the next section of the agenda, where we'll be talking about astronomy, about what's up in the sky, and other agenda items as well. So do come back in about 10 minutes. So that, let's say 8:40, 8:45. Okay, welcome back to the second part of the meeting. For the first agenda item, we've got Aaron Thiro, who's going to be talking about what's up in the sky.
Hear me? Lean in. Oh, man. All right, what's up in the sky? July 14th through August 11th. I wanted to say something about CDT. I know we're in Central Time Zone. I just put CDT here because it's Central Daylight Savings Time, which I had to actually put into Stellarium, or else it gave me a false time for everything. This is the moon phases this month. The picture was actually taken by Tyler Lucio. He allowed me to use it for this presentation. Third quarter moon, July 25th, full moon, August 1st. And the cool thing about August is there's going to be a blue moon, which just means 2 full moons in the same month. First quarter, August 8th. Venus is going to be up. It's kind of getting lower in the sky this month. It'll continue to be with Mars for a little while. And actually happening tonight at 9:33, if you get out of here quick enough and you go look to the western sky, the International Space Station is going to whiz by Venus. So if we get out of here quick enough, you'll be able to see this. Jupiter is will rise at 1:51 a.m. today. It's getting pretty bright. It's still early in the morning, but you can see it. It's pretty apparent. I've seen it through the telescope a few times. It's not super large right now, but it's large enough. The apparent size. Saturn has been slowly rising earlier in the day. It actually crosses the meridian now at nighttime, which is at 4:24 a.m. at an altitude of 49 degrees. Uranus. I have not seen Uranus this year. I saw it last year, but it is starting to rise at 2:23 a.m. You will need a telescope to see this. If you need some help finding it, August 8th, it'll be near the moon and Jupiter and Aldebaran. It'll kind of make a little thingamajig there. Neptune will also need a telescope to view it. It'll be near the moon on August 5th, early in the morning. And here's some of the other things besides planets. The Perseids are going to be starting they're July 14th to September 1st. They peak on August 12th to the 13th, the night of that. It's usually, there's a lot of them. It's hard to see in the city limits, but I tell you what, I just drove over to Bolivar Peninsula this weekend. It gets pretty dark out there. I actually saw the Milky Way for the first time in a minute out here. So that was pretty nice. Also, the Eagle Nebula, I actually saw, no, I didn't see this one for the weekend, but the Eagle Nebula is another object that's real nice to see. It's a H2 region. I think you can see this one with naked eye if you're in dark enough skies. And this Perseus globular cluster will be high in the sky really late at night. If you live kind of like I do, where I'm kind of up all night. It's the first globular cluster I've ever seen, and it's pretty good in a telescope. Oh, and Ptolemy's cluster. This is an open star cluster in Scorpio and Sagittarius. This one you can see without a telescope. It's pretty great. I think this is what I saw over the weekend.
Thanks, Aaron. A lot of old favorites there that I've seen myself. If you haven't done Uranus and Neptune, in a telescope, particularly a refractor, which is my favorite. They are just a hoot to do. They're really small, even under a lot of magnification. But when you start to see how orb-like those planets are, and you see them as orbs, and you see them as either blue or kind of green, depending on your own eye, they're just so much fun to see, and you just can't take your eye off it. So I actually really enjoy doing planets like that. So thanks for pointing that out, Aaron. Next up. This is a slide I just put in there. I think about last month or the month before, we had a presentation about the United Space School. Well, that program is started. It's about a week into the program for the Space School kids. I think there's about 40 or so 16 to 18-year-olds going through this program of education right now. I think it finishes up around about the 30th of July, the end of this month. That's going on right now. Johnson Space Center Astronomy Society, we're going to be sponsoring an event for them on the 22nd of July, which is a week on Saturday. There's going to be presentations from some of the club members, and there's also going to be some other presentations from others as well, and an astronaut and things like that. So we got an event that's taking shape. That's actually going to be followed by a star party in the League City area. Dan Roy, one of the club members, is going to be doing that locally, just as he did for the Space School last year as well. It's an open event, obviously, for the Space School kids, of which there are around about 40 or so. It's also open to JSC AS members, if you'd like to come along. Food is going to be provided, plated food and everything. It's actually going to be at the South Shore Harbor Country Club, and starting on the dot at 7 p.m. So if you want to go, and please take a note of that address and come along. Aaron.
So you need volunteers for this?
Absolutely. We could definitely use some if you want to connect with us afterwards.
What time should volunteers show up?
6:15.
Sounds great. I'll be there.
Excellent. Star Party News with David Howland.
All right, I'm now one of the few people keeping you between now and pizza. So, all right, June 24th, we had an event at Hack Winery Star Party on a Saturday. I've got slides about that. Chris just got through mentioning it. United Space School Star Party in League City. If you're available that night, club would appreciate you going out and helping out. Do check your sunset and twilight times too. On August 26th, the Saturday, we're going to have another event at the Hack Winery toward the end. A few more dates are going to be on the calendar. I've got to work that out with Anthony. Then all the way to September 8th to 16th, there's going to be the Okotek Star Party that some will go to. And then this one is still stargazing at Evelyn Metter Library in Seabrook is under discussion. I was about ready to commit to dates, and she said, "Oh, our June and July are already taken." And I was talking to her at the end of May, so she wants to talk about more April, September. And as I said, here 3 more dates are planned with the winery. Aaron, I'm glad you reminded me about the Persids. I had somebody from Harris County wanting to do a Persid event over at just dropped it. That park that's off of Nassau Road 1 on the, sorry, Nassau Road 1 on the other, excuse me, Challenger Park. And I've got to try to tell that person that with the city lights there, it's not going to work. They really need to go to the George, go east, or go where you went to, Galveston or Boulevard in order to be able to see them. They want to know if the club wanted to come out and do it. And Connie and I have done meteor showers, and they're just so faint, and the urban lights will just kill it. All right, Hack Winery, June 24th. I want to thanks to Chris Randall, Reed Klotzer, Bob and Leslie Eaton, and Connie and I were there. Some 125 or so is in attendance. Don't let the pictures fool you. It was blazing, and we were sweating crazily. Chris is getting his big boy tuned up. Reed's here, futzing, getting his big scope ready. You can kind of see the glistening on Connie's face here. Leslie was busy doing something, I'm not sure, but she was also there with her scope. I think Chris over here was either, I think, on Venus perhaps, given the daylight. And as things progressed, we ended up into the moon, because inside daylight savings time, I always try to keep a first quarter moon-ish something available so we can see. Now, I was talking to a gentleman out in the foyer at the break. These two people were literal walk-ons. They just showed up and I dropped their names. I need to write these things down. They had this scope, got it set up. They needed some help getting it set up, and that's exactly what we did. We got our help set up, going, and they were actually able to do some viewing. And then once I think she was on the moon, they were able to start showing people the moon through her scope. They were pretty happy with how it all turned out. But as you can see here, it starts getting darker, and we had a bunch of people around various scopes. And here's Reed's scope here. And then, yeah, we have to deal with the lights a little bit with the hack winery, but that's sort of the fun and games with it. But overall, it was a good fun event. And Melanie dates a black hole when we have nothing in common, but I'm strangely attracted to. So that's all.
Okay, door prizes time. Excellent. Choice of three things: moon map, astronomy, that's the reason I'm making you do it. So I can struggle. Excellent. Thank you all for being here. Don't forget Mod Pizza, the event after the event. So go to that if you can and join us there. And we'll see you again second Friday in this location in August. Thanks ever so much.